In 1964, astronomers detected X-rays coming from Cygnus X-1, a source so intense and so impossible that it should not exist according to our understanding of physics. For centuries, scientists had theorized about objects whose gravity could trap even light itself. But this was the first time we found strong evidence that these cosmic monsters were real. Deep within the mathematics of Einstein's equations, buried in solutions that physicists initially dismissed as mathematical curiosities, lies evidence of phenomena so bizarre that they challenge the very foundations of space, time, and reality itself. What if black holes are not the simple gravitational wells we imagine, but gateways to physics we cannot comprehend? What if the information paradox that has haunted physicists for 50 years reveals that our most fundamental laws of nature are incomplete? What if falling into a black hole doesn't mean death, but transformation into something we cannot yet understand? Today we journey through 101 weird facts about black holes that reveal why these objects may be the strangest and most important phenomena in the entire universe. Prepare yourselves. We begin. The term black hole itself was not coined until 1967 by physicist John Wheeler. Before this, these objects were called frozen stars or collapsed stars, names that failed to capture their true nature. Wheeler's terminology stuck precisely because it evoked the profound darkness and inescapability that defines these objects. The name itself reveals a truth we often overlook. These are not holes at all, but objects so massive and compressed that they create regions of space-time from which escape is physically impossible. Black holes are described by only three parameters: mass, angular momentum, and electric charge. This remarkable simplicity led physicist John Archibald Wheeler to declare that black holes have no hair, meaning they carry almost no information about the matter that formed them. A black hole created from the collapse of a star, made entirely of iron, would be indistinguishable from one created by the collapse of a star, made entirely of helium, provided they have the same mass, spin, and charge. The no-hair theorem appears to violate quantum mechanics by destroying information. If you throw a book into a black hole, all the specific information encoded in that book seems to vanish from the universe forever. This creates the information paradox that has haunted theoretical physics since Stephen Hawking first described it in 1975. The paradox suggests either that information can be destroyed, violating quantum mechanics, or that general relativity's description of black holes is incomplete. Recent calculations by Xavier Calmet and Stephen H. Su reveal that black holes actually have quantum hair. When quantum gravitational corrections are included in the mathematics, black holes preserve subtle quantum information about the matter that formed them. This quantum hair stores information in the gravitational field surrounding the black hole in ways that previous calculations had missed entirely. The discovery suggests that information is not destroyed, but encoded in patterns so subtle that they require quantum gravity to detect. The Page curve describes how the entropy of Hawking radiation should behave if information is preserved during black hole evaporation. Don Page predicted in 1993 that if black holes preserve information through unitary evolution, the entropy of the radiation should initially increase, reach a maximum at about half the black hole's lifetime, then decrease back to zero when evaporation is complete. For decades, no one could derive this curve from first principles using standard physics. In 2019, two independent research groups simultaneously demonstrated how to derive the Page curve using quantum extremal surfaces. The calculation requires considering not just the Hawking radiation escaping from the black hole, but also quantum entanglement patterns that connect the radiation to the black hole's interior. The derivation represents the closest physicists have come to resolving the information paradox that has persisted for nearly half a century. Quantum extremal surfaces are boundaries in space-time that suddenly materialize inside black holes as they evaporate. These surfaces initially have no effect on the system, but eventually become the dominant factor determining the entropy of the Hawking radiation. The surfaces appear abruptly, like a phase transition similar to water freezing into ice, marking a fundamental change in the physics governing the evaporating black hole. The quantum extremal surface splits the universe into two distinct regions. One region remains equivalent to the distant boundary of spacetime, where observers measure the Hawking radiation. The other becomes a dragon's realm, about which external observers can have no information. This split indicates that radiation bleeding from the system is fundamentally altering its information content in ways that classical general relativity cannot describe. Entanglement islands are regions inside black holes that maintain quantum entanglement with the Hawking radiation outside. These islands can extend slightly beyond the event horizon, though by distances smaller than the Planck length, making them extraordinarily difficult or impossible to measure directly. The islands contain copies of information that appears to be duplicated, potentially explaining how information escapes while also remaining inside the black hole without violating quantum mechanics' no-cloning theorem. Raphael Busso and Jeff Pennington calculated that for realistic rotating and charged black holes, entanglement islands extend much farther beyond the event horizon than in simpler models. The extended islands make the physics potentially testable, though the experiments required would be extraordinarily difficult to perform. Testing would require sending a probe extremely close to the event horizon and analyzing quantum correlations in ways that exceed current technological capabilities by enormous margins. The firewall paradox emerged in 2012 when researchers discovered scenarios where complementarity leads to violations of quantum mechanics. The AMPS paper, Almheri, Marolf, Polchinski, and Sully, proved that an observer could potentially access two entangled copies of the same quantum information, violating the no-cloning theorem. This violation requires either that a firewall of intense radiation forms at the event horizon, destroying anything that crosses, or that our understanding of black hole interiors is fundamentally wrong. Frozen star models propose that black holes are not actually black holes at all, but ultra-compact objects whose collapse is frozen by quantum effects just before event horizon formation. These objects would be composed of matter whose quantum properties prevent complete gravitational collapse to a singularity. Frozen stars lack both event horizons and singularities, potentially resolving the information paradox by avoiding the conditions that create it. Theoretical analysis of frozen stars shows they behave as nearly perfect absorbers, despite lacking event horizons. The objects can absorb almost everything that falls onto them and generate gravitational waves indistinguishable from those produced by classical black holes. The similarity in observable properties means that most astronomical observations cannot distinguish between frozen stars and traditional black holes, leaving the question of their true nature unresolved. Black holes exert pressure on their surroundings, despite being vacuum solutions to Einstein's equations. Research published in 2021 demonstrated for the first time that the quantum vacuum fluctuations near a black hole's event horizon create a measurable outward pressure. This pressure is tiny for stellar mass black holes, but becomes significant for microscopic black holes, if they exist. The discovery reveals that black holes are more complex objects than the bald description suggests. Spaghettification is the formal name for the tidal forces that stretch objects falling into black holes. The gravitational gradient increases so dramatically near small black holes that the difference in gravitational pull between your head and feet would be millions of times stronger than Earth's gravity. The tidal forces don't just stretch objects vertically, they also compress them horizontally, creating a combination of elongation and compression that thoroughly destroys any structure. For supermassive black holes, spaghettification occurs inside the event horizon rather than outside it. An astronaut falling into a supermassive black hole like Sagittarius A would cross the event horizon without experiencing deadly tidal forces. The astronaut would survive intact for several more seconds, or even minutes before finally being torn apart much closer to the central singularity. This counterintuitive fact means larger black holes are paradoxically safer than smaller ones for anyone unfortunate enough to fall in. The Schwarzschild radius defines the size of a black hole's event horizon for non-rotating black holes. This radius is directly proportional to the black hole's mass, according to the formula RS Chern 2gmc2. For a black hole with the mass of our Sun, the Schwarzschild radius is approximately 3 kilometers. For a supermassive black hole of 4 million solar masses like Sagittarius AI, the Schwarzschild radius extends to roughly 12 million kilometers, nearly 8 times the radius of the Sun. Time dilation near black holes becomes extreme as objects approach the event horizon. For an observer far from the black hole, an infalling object appears to slow down progressively, never quite crossing the horizon. The object's image becomes increasingly redshifted and dim, eventually fading from view entirely within a fraction of a second. This effect means that, from an external perspective, the universe has never actually seen anything cross an event horizon. All the matter that formed black holes and everything that has fallen into them since appears frozen just above the horizon. From the perspective of an infalling observer, crossing the event horizon happens in finite time with nothing particularly special marking the moment of crossing. For a stellar mass black hole, the journey from event horizon to central singularity takes only a fraction of a second by the infalling observer's clock. For a supermassive black hole, this journey could last several seconds or even minutes, providing ample time to contemplate one's fate before the inevitable destruction. The interior of a rotating black hole differs dramatically from non-rotating solutions. Roy Kerr's solution to Einstein's equations revealed that rotating black holes possess not one, but 2 event horizons. Between these horizons lies the ergosphere, a region where space-time itself is dragged around the black hole faster than the speed of light. Within the ergosphere, remaining stationary becomes physically impossible. The rotating space-time forces all objects to move in the direction of the black hole's rotation. The Penrose process allows energy extraction from rotating black holes through interactions in the ergosphere. A carefully constructed physical process can extract rotational energy from the black hole, in principle allowing civilizations to harvest enormous amounts of power from supermassive black holes. The process works by allowing objects to shed angular momentum into the ergosphere, while escaping with more energy than they entered with, gradually slowing the black hole's rotation. The ring singularity at the center of a rotating black hole differs from the point singularity in non-rotating holes. The rotation creates a ring-shaped region of infinite density and curvature rather than a single infinitely dense point. Theoretical calculations suggest that the ring singularity might allow travel through the black hole to other regions of space-time. Though whether this represents physical reality or merely a mathematical artifact remains unknown. Wormholes emerge as mathematical solutions in some rotating black hole geometries. These connections between distant regions of space-time or even between different universes appear in the equations describing maximally extended Kerr black holes. However, the wormholes that appear in these solutions are unstable and would collapse before anything could travel through them. Keeping a wormhole open for travel would require exotic matter with negative energy density, which may not exist in nature. The interior geometry of black holes changes character at the event horizon. Inside the horizon, the roles of space and time effectively exchange. The direction toward the singularity becomes a temporal direction rather than a spatial one. Moving toward the singularity is as inevitable as moving forward in time for objects outside the horizon. This exchange means that asking, "Where is the singularity?" becomes meaningless. The correct question is, when is the singularity? Primordial black holes could have formed in the early universe from quantum fluctuations during the Big Bang. These hypothetical objects would have masses ranging from microscopic to millions of solar masses, depending on when and how they formed. Unlike stellar black holes, which require stars to form and die, Primordial black holes could exist at any mass scale, including masses far smaller than any star could produce through collapse. Some primordial black holes may have completely evaporated through Hawking radiation by now. Black holes smaller than about 10 to 11 kilograms would have evaporated during the 13.8 billion years since the Big Bang. The final moments of this evaporation would produce intense bursts of gamma radiation as the remaining mass converts entirely to energy. No such evaporation events have been definitively observed, placing constraints on how many microscopic primordial black holes could exist. The possibility that microscopic primordial black holes constitute dark matter has been seriously considered. These objects would interact only gravitationally, never emitting light or other electromagnetic radiation, making them perfect dark matter candidates. However, careful analysis of gravitational lensing observations and other astronomical data has ruled out primordial black holes as the dominant component of dark matter across most possible mass ranges. A narrow window of possibilities remains open for specific mass ranges. Microscopic black holes might be passing through Earth and your body right now. If primordial black holes in certain mass ranges exist, they would be zipping through ordinary matter continuously, leaving only microscopic traces of their passage. These tiny black holes would pass through the entire planet without even slowing down, leaving tunnels of disrupted matter too small to detect with current technology. The search for primordial black holes involves looking for their gravitational effects rather than the objects themselves. Astronomers search for characteristic patterns in the gravitational lensing of background stars that would reveal compact objects of specific masses passing through the line of sight. Recent surveys have found tantalizing hints of lensing events that could represent primordial black holes, though alternative explanations cannot be ruled out. Supermassive black holes exist at the centers of nearly all large galaxies. These monsters contain millions to billions of times the mass of our Sun, compressed into regions smaller than our solar system. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius AX, has a mass of approximately 4 million suns. Despite this enormous mass, its event horizon spans only about 12 million kilometers, small enough to fit comfortably inside Mercury's orbit. The fastest growing black hole ever discovered is consuming matter at more than 40 times the theoretical limit. This object, existing just 1.5 billion years after the Big Bang, is growing so rapidly that it challenges our understanding of how supermassive black holes form. The Eddington limit describes the maximum rate at which a black hole should be able to accrete matter. Beyond this limit, radiation pressure from the infalling material should blow away additional matter before it can fall in. James Webb. Space telescope observations revealed a voraciously feeding supermassive black hole in the infant universe just 570 million years after the Big Bang. This black hole sits at the heart of galaxy Cygnus LRD Z8.6, one of the little red dot galaxies that JWST has been routinely discovering since beginning operations. The black hole is growing far faster than theoretical models predict should be possible in such a young galaxy at such early cosmic times. The most massive black hole ever detected may be a monster weighing 36 billion solar masses. Located in one of the most massive galaxies ever seen, 5 billion light-years from Earth. This black hole has competition from Phoenix A, estimated to have a mass around 100 billion suns. Measuring the masses of such enormous objects at great distances involves significant uncertainties, making it difficult to determine which truly holds the record. The most distant black hole flare ever observed erupted from a galaxy 10 billion light-years away. The flare, designated J2245+3743, pumps out energy equivalent to the output of 10 trillion suns. The immense power output makes this one of the most luminous events ever detected, visible across most of the observable universe. The flare resulted from a tidal disruption event, where a star wandered too close to the black hole and was torn apart. Tidal disruption events occur when stars pass within the tidal radius of a black hole and are ripped apart by gravitational forces. For a star like our Sun approaching a supermassive black hole, tidal disruption would occur at a distance of roughly 1 astronomical unit, about the current distance from Earth to the Sun. The disruption process is violent and asymmetric, with some of the stellar material being ejected at high velocities, while the rest spirals into an accretion disk around the black hole. The first tidal disruption event observed breaking through a star's surface was recorded in 2024. Supernova SN 2024 GGI revealed a surprisingly olive-shaped blast when studied shortly after the explosion began. The asymmetric shape indicates that the explosion broke through different parts of the stellar surface at different times, creating a complex geometry that challenges simple spherical explosion models. Binary black hole systems involve two black holes orbiting each other in increasingly tighter spirals. As the black holes orbit, they emit gravitational waves that carry away orbital energy, causing the orbit to decay. The decay continues until the black holes merge in a final catastrophic collision that converts a significant fraction of their combined mass directly into gravitational wave energy. LIGO detected the first gravitational waves from merging black holes on September 14, 2015. The signal arrived from two black holes with masses of approximately 36 and 29 solar masses merging 1.3 billion light-years away. The merger converted roughly 3 solar masses of matter entirely into gravitational wave energy in a fraction of a second, briefly outshining the entire visible universe in gravitational radiation. Two black hole mergers, observed just weeks apart in late 2024, opened extraordinary new windows into the universe's most extreme events. These collisions provided detailed information about how black holes with very different mass ratios merge and how much energy they convert into gravitational waves. The observations confirmed theoretical predictions about black hole ringdown, the characteristic vibrations that the merged black hole undergoes as it settles into a stable configuration. Black hole triple systems have been discovered containing a black hole with 2 orbiting companions. The system V404 Cygnus includes a black hole orbiting a normal star, with a second, more distant star in a much wider orbit around the pair. The triple system configuration constrains theories of how the black hole formed. The distant companion star could not have survived if the black hole formed through a standard supernova explosion that would have kicked the system apart. The discovery of the first binary stars orbiting the Milky Way's supermassive black hole revealed that stable stellar systems can exist even in the extreme environment near Sagittarius A. These stars orbit each other, while simultaneously orbiting the black hole in the chaotic gravitational environment of the galactic center. The binary survival indicates that the region near the central black hole is less disruptive than some models had predicted. Magnetic fields around black holes show remarkably organized structures despite the chaotic violence of the accretion process. Observations of Sagittarius A revealed magnetic field patterns similar to those seen around the much more massive M87E. The organized fields suggest that magnetic forces play crucial roles in launching jets from some black holes, while other black holes with similar field structures show no evidence of jets at all. Jets launched from black holes can extend for millions of light-years across intergalactic space. These enormous streams of matter and energy flow at velocities approaching the speed of light, powered by the extraction of rotational energy from spinning black holes. The jets interact with surrounding gas on galactic scales, influencing star formation across entire galaxies and even throughout galaxy clusters. The most powerful winds ever detected from a black hole blow at speeds exceeding 130 million miles per hour. These ultra-fast outflows carry enormous amounts of matter and energy away from active galactic nuclei, depositing this material into the surrounding galaxy. The winds play critical roles in regulating how galaxies evolve by limiting star formation and enriching intergalactic space with heavy elements. Active galactic nuclei are powered by supermassive black holes actively consuming matter. The accretion process releases enormous amounts of energy as matter spirals inward, heating to millions or even billions of degrees before crossing the event horizon. Active galactic nuclei can outshine their entire host galaxies by factors of thousands, making them visible across most of the observable universe. Quasars are the most luminous persistent objects in the universe, powered by supermassive black holes consuming matter at enormous rates. The brightest quasars shine with the light of trillions of stars from objects smaller than our solar system. Quasars were much more common in the early universe than today, suggesting that supermassive black holes were growing most rapidly during the universe's first few billion years. The fastest feeding black hole eats a sun a day. This object, one of the fastest growing black holes ever discovered, consumes the equivalent of one solar mass every 24 hours. The accretion process releases enormous amounts of radiation as the infalling matter heats up, creating one of the most luminous objects in the distant universe. The black hole has taken 12 billion years for its light to reach us, showing us conditions when the universe was less than 2 billion years old. Numerical simulations of black hole accretion have reached new levels of sophistication by fully accounting for both Einstein's theory of gravity and the dominant role of radiation. These simulations reveal that near the black hole, the accretion flow forms a dense thermal disk embedded within a magnetically dominated envelope. The thermal disk structure remains remarkably stable, despite the extreme radiation pressure and turbulent conditions. The accretion disk around a black hole is not truly disk-shaped at all scales. Recent simulations show that the disk consists of different zones with distinct physical properties. Near the black hole, a geometrically thin but optically thick thermal disk dominates. Farther out, a geometrically thick advection-dominated accretion flow channels matter inward. The transition between these zones depends on the accretion rate and the black hole's spin. Black holes' shadows were first imaged by the Event Horizon Telescope in 2019. The shadow of M87 revealed a dark circular region surrounded by a bright ring of emission from hot gas in the accretion disk. The size and shape of the shadow precisely matched predictions from general relativity, providing strong confirmation that these objects are indeed the black holes described by Einstein's theory. The image of Sagittarius A's shadow was much more difficult to obtain than M87, despite being much closer. Sagittarius A is roughly 2,000 times smaller than M87T, and its accretion disk varies on timescales of minutes rather than days. The rapidly changing emission required new analysis techniques that could synthesize images from data where the source itself was changing during the observations. Intermediate mass black holes, with masses between 100 and 100,000 solar masses, have been extremely difficult to find. These objects should exist as the missing link between stellar mass and supermassive black holes, but definitive detections remain rare. The first direct detection of an intermediate mass black hole came from LIGO's observation of gravitational waves from a merger producing a black hole of about 142 solar masses. The final parsec problem describes the difficulty in getting binary supermassive black holes to merge after galaxy collisions. When two galaxies merge, their central black holes initially spiral together through dynamical friction with surrounding stars. However, this process stalls when the black holes reach separations of about 1 parsec, apparently unable to close the final gap. Recent calculations suggest that interactions with dark matter particles may provide the missing mechanism to complete the merger. Dark matter may have helped make supermassive black holes in the early universe. The presence of dark matter can trigger direct collapse of gas clouds into black holes without forming stars first. This process could create seed black holes with masses of thousands or even millions of suns right from the start, giving them a head start in growing to supermassive scales before the universe was 1 billion years old. Some black holes may have formed from the direct collapse of gas clouds in the young universe. These direct collapse black holes would skip the star formation stage entirely, creating supermassive seed black holes of 10^4 to 10^6 solar masses. The process requires very specific conditions, including metal-free gas and intense radiation to prevent the gas from fragmenting into stars. But such conditions may have been common in the early universe. New simulations suggest magnetic fields hold the key to forming black holes that defy known mass limits. When powerful magnetic forces act on a collapsing spinning star, they eject vast amounts of material while allowing the core to continue collapsing. The ejected material carries away mass and angular momentum, potentially allowing the formation of black holes much more massive than standard supernova models permit. Stellar mass black holes typically form from stars more than 20 times the mass of our Sun. When these massive stars exhaust their nuclear fuel, their cores collapse catastrophically in supernova explosions. If the core mass exceeds about 3 solar masses, electron degeneracy pressure and neutron degeneracy pressure cannot halt the collapse, and the core continues collapsing until it forms a black hole. The smallest possible stellar mass black hole has a mass around 3 solar masses. Below this mass, quantum degeneracy pressure can support the collapsed object as a neutron star. The exact lower limit depends on the equation of state of nuclear matter at extreme densities, which remains uncertain. Recent observations have found several compact objects with masses in the range between 3 and 5 solar masses, where the distinction between the most massive neutron stars and the least massive black holes becomes blurred. Black holes could be natural particle accelerators that replicate the colossal energies of human-built colliders. The extreme gravitational and electromagnetic fields near black holes can accelerate particles to energies far exceeding what we can achieve on Earth. These natural accelerators might produce signatures of dark matter or other exotic physics that would be impossible to observe any other way. Cosmic rays from black hole jets may carry signatures of physics beyond the standard model. The highest energy cosmic rays detected on Earth have energies exceeding 10⁻20 electron volts, far beyond what any human-built accelerator can achieve. Some of these ultra-high energy cosmic rays may originate from particle acceleration in jets launched by supermassive black holes, providing a window into physics at energy scales we cannot reach artificially. Black holes may serve as the universe's ultimate information storage system. Recent theoretical work suggests that the quantum hair surrounding black holes encodes information with far greater density than any system we can construct. The information is stored in correlations between quantum states of the gravitational field itself, potentially allowing the universe to archive vast amounts of data in these compact objects. The holographic principle suggests that black holes encode all their information on their two-dimensional event horizon surfaces. The information content of a black hole scales with the area of its event horizon rather than its volume, a surprising result that has profound implications for quantum gravity. This principle has been extended to suggest that our entire three-dimensional universe might be a holographic projection of information encoded on a distant two-dimensional surface. ADS-CFT correspondence connects black holes in curved anti-de Sitter spacetime to quantum field theories on the boundary of that spacetime. This mathematical correspondence allows physicists to translate difficult quantum gravity problems into more tractable quantum field theory calculations. The correspondence has provided crucial insights into the information paradox by showing explicitly how black holes in ADS space preserve information unitarily. Black holes may actually be fuzzball configurations in string theory, rather than classical general relativity objects. In this picture, the smooth event horizon of classical black holes is replaced by a stringy quantum fuzz extending over the entire region where the horizon would be. The fuzzball picture potentially resolves the information paradox by eliminating the horizon, where information would be lost. The mass of a black hole determines its surface area according to A Chadar 16 PG2 M2 Ta C4. This relationship means that merging two black holes of equal mass creates a final black hole whose area exceeds the sum of the original two areas. The area increase reflects the conversion of mass to gravitational wave energy during the merger. The lost mass shows up as a smaller final surface area than the sum of the initial areas. Hawking radiation causes black holes to slowly evaporate over immense timescales. A black hole with the mass of our Sun would take approximately 10^67 years to evaporate completely, far longer than the current age of the universe. Supermassive black holes will persist even longer, with lifetimes exceeding 10 or 100 years for the most massive examples. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Stellar mass black holes emit radiation, with temperatures of mere billionths of a degree above absolute zero. This radiation is so weak that it is completely overwhelmed by the cosmic microwave background radiation that fills the universe. Only microscopic black holes would be hot enough for their Hawking radiation to be detectable. The final moments of black hole evaporation are predicted to be explosive. As the black hole shrinks, its temperature increases, causing it to radiate faster. This runaway process continues until the final mass converts entirely to energy in a brilliant flash of gamma radiation. The explosion from a black hole of initial stellar mass would convert roughly 10 to 31 kilograms of matter to energy, equivalent to millions of hydrogen bombs. Black holes are the most efficient known energy conversion mechanism in the universe. Accretion onto a black hole can convert more than 40% of the infalling matter's mass energy into radiation and kinetic energy. This efficiency far exceeds the approximately 1% efficiency of nuclear fusion in stars. The extreme efficiency makes black holes the most powerful persistent energy sources in the cosmos. Spinning black holes can convert up to 29% of their mass energy into rotational energy that can be extracted through the Penrose process. This theoretical upper limit, known as the Christodoulou bound, represents the maximum energy that can be extracted from a rotating black hole before it becomes non-rotating. Advanced civilizations might harvest this energy to power themselves for billions of years. The largest known black hole shadow has been measured at roughly 40 billion kilometers across. This shadow cast by the supermassive black hole M87T is visible from Earth despite being 55 million light-years away. The shadow appears as large as it does because of the black hole's enormous mass of 6.5 billion suns, creating a correspondingly enormous event horizon. Gravitational lensing around black holes creates multiple images of background objects. Light passing close to a black hole is bent by the intense gravitational field, creating ring-like patterns known as Einstein rings when the alignment is perfect. The photon sphere at 1.5 times the Schwarzschild radius marks the location where light can orbit the black hole in unstable circular paths. The photon sphere is the last stable orbit for light around a non-rotating black hole. Any photon that crosses inside this boundary will either fall into the black hole or escape to infinity. No stable circular orbits exist closer to the horizon. For rotating black holes, the photon sphere is replaced by a more complex structure where the stability of photon orbits depends on the direction of motion relative to the black hole's spin. The innermost stable circular orbit, ISCO, for massive particles occurs at 3 times the Schwarzschild radius for non-rotating black holes. Objects orbiting closer than the ISCO will spiral inward unstably, unable to maintain circular orbits regardless of their velocity. For rotating black holes, the ISCO can be as close as 1 Schwarzschild radius for objects orbiting in the direction of the black hole's spin, allowing matter to orbit much closer before falling in. Relativistic beaming causes jets from black holes to appear much brighter when pointed toward us. When a jet moves at near-light speed directly toward our line of sight, its emission is concentrated and blue-shifted, making it appear far more luminous than it would if viewed from the side. This effect can make the same black hole appear thousands of times brighter or fainter, depending on the viewing angle of its jets. Frame dragging near rotating black holes forces all nearby objects to orbit in the direction of the black hole's rotation. This effect, predicted by general relativity, becomes extreme in the ergosphere of a Kerr black hole. The rotation of spacetime itself becomes so severe that remaining stationary relative to distant stars becomes physically impossible. You must orbit the black hole, whether you want to or not. Quasi-periodic oscillations, observed in X-ray emissions from black hole accretion disks, may reveal the black hole's spin rate. These characteristic frequencies depend on the structure of the innermost stable circular orbit, which in turn depends on the black hole's angular momentum. By identifying multiple frequencies and their relationships, astronomers can infer both the black hole's mass and its spin. Some black holes spin at nearly the maximum rate allowed by general relativity. Measurements suggest that certain supermassive black holes rotate at more than 98% of the theoretical maximum spin. At these extreme rotation rates, the ergosphere extends far from the event horizon, and the innermost stable circular orbit approaches very close to the horizon, allowing extremely efficient energy extraction from infalling matter. Naked singularities, if they exist, would be singularities without event horizons. The cosmic censorship conjecture suggests that nature prevents such objects from forming. All singularities should be hidden behind event horizons. However, certain solutions to Einstein's equations do allow naked singularities under specific circumstances, and whether they can actually form in realistic physical processes remains an open question. The weak cosmic censorship hypothesis states that singularities visible to distant observers cannot form from realistic collapse. This hypothesis remains unproven, but is widely believed by physicists based on the behavior of known solutions to Einstein's equations. Proving or disproving cosmic censorship represents one of the major outstanding problems in general relativity. Traversable wormholes would require exotic matter with negative energy density to remain open. Quantum field theory allows such matter to exist temporarily through quantum effects, like the Casimir effect. But creating enough exotic matter to support a human traversable wormhole appears to require physics beyond our current understanding. Most physicists believe that traversable wormholes, while mathematically possible, cannot exist in the actual universe. The ER-EPR conjecture proposes that quantum entanglement and wormholes are actually the same phenomenon. According to this radical idea, any two entangled quantum particles are connected by a microscopic wormhole through space-time. This connection between quantum mechanics, EPR, Einstein-Podolsky-Rosen entanglement, and general relativity, ER, Einstein-Rosen bridges or wormholes, suggests a deep unity in physics that we are only beginning to understand. Black holes may be responsible for enriching the universe with heavy elements. The extreme conditions in accretion disks and jets allow nuclear processes that produce heavy elements more efficiently than stellar nucleosynthesis. Material ejected from black hole systems through jets and winds carries these heavy elements throughout galaxies, contributing to the chemical evolution that makes planets and life possible. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This result, known as the Bekenstein-Hawking entropy, reveals that black holes are the most entropic objects possible for their size. The enormous entropy has profound implications for the second law of thermodynamics and suggests that black holes represent the ultimate endpoint of gravitational collapse. Black holes may solve the cosmological constant problem by removing vacuum energy from the universe. Some theoretical proposals suggest that black holes filter out vacuum energy that would otherwise cause space to expand catastrophically fast. This mechanism could explain why the observed vacuum energy density is so much smaller than quantum field theory predicts. The membrane paradigm treats the event horizon as if it were a physical membrane, with definite properties like conductivity and viscosity. This mathematical technique allows complex calculations about black holes to be performed more easily by treating the horizon as a boundary with specific physical characteristics. The paradigm has proven remarkably effective for understanding black hole electrodynamics and thermodynamics. Gravitational wave echoes might reveal the true quantum structure of black hole horizons. If the event horizon is not a perfectly smooth surface but has quantum structure at tiny scales, gravitational waves from mergers might reflect off this structure and produce detectable echoes. Searches for such echoes in LIGO data have produced tantalizing but inconclusive results. Black hole bombs can extract energy from rotating black holes through superradiant amplification of waves. When waves with certain frequencies enter the ergosphere of a rotating black hole, they can be amplified and extract rotational energy. Building a reflective cavity around the black hole would cause the amplification to repeat exponentially, creating an energy extraction mechanism or a potential bomb. The largest ever map of active supermassive black holes, released in 2024, charted an unprecedented volume of the universe. The survey identified hundreds of thousands of quasars, revealing how the population of actively feeding black holes has evolved over cosmic history. The map shows that black holes were most active when the universe was between 2 and 4 billion years old. Changing-look quasars can transition between active and inactive states on timescales of years. These objects challenge our understanding of black hole accretion, which should vary on much longer timescales according to standard models. The rapid changes suggest that accretion disks can be disrupted and rebuilt on surprisingly short timescales through mechanisms we don't fully understand. Two massive black holes discovered eating away at the same galaxy reside at different distances from the galactic center. One black hole sits at the galaxy's core, as expected. The second, located 2,600 light-years away from the center, was revealed by a tidal disruption event, where it tore apart a star. The unusual configuration suggests a complex merger history for this galaxy. The universe may be filled with rogue black holes wandering through intergalactic space. When galaxies merge, gravitational interactions can eject black holes at high velocities, sending them careening through the cosmos. These rogue black holes would be essentially invisible unless they happen to consume nearby matter, making them extraordinarily difficult to detect and catalog. Black holes provide the loudest sounds ever created in the universe, though we cannot hear them directly. The gravitational waves from merging black holes carry information about the chirp as the black holes spiral together. If we could hear these gravitational waves as sound, they would build from a low rumble to a high-pitched tone over fractions of a second, creating the most powerful acoustic event conceivable. The shadow of a black hole appears larger than the event horizon due to light-bending effects. The strong gravitational lensing causes the shadow to extend to approximately 2.6 times the Schwarzschild radius. This photon sphere shadow is what the Event Horizon Telescope images actually show, not the event horizon itself, which cannot be directly observed. Computational astrophysicists have reached a turning point in black hole research by creating the most detailed simulations yet of luminous black hole accretion. These simulations fully account for both Einstein's gravity and radiation's dominant role without relying on simplifying shortcuts. The results reveal a remarkably stable thermal disk structure, despite extreme turbulence and radiation pressure. Black holes may be testing grounds for quantum gravity, the long-sought theory unifying quantum mechanics and general relativity. The extreme conditions near event horizons and singularities cannot be described by either theory alone. Resolving the contradictions between the two theories in the context of black holes may finally reveal the correct quantum theory of gravity. The universe's ultimate fate may involve black holes becoming the last remaining macroscopic structures. In the distant future, after all stars have died and galaxies dispersed, black holes will be the only objects remaining. These black holes will slowly evaporate through Hawking radiation until finally even they disappear, leaving behind only a cold, empty, expanding universe. The singularity at a black hole's center may not actually be infinitely dense. Quantum gravity effects should become important at the Planck scale, possibly preventing the formation of true mathematical singularities. The actual structure of the black hole core may be a quantum foam of spacetime that cannot be described by classical general relativity. Black holes challenge our most fundamental understanding of space, time, and the nature of reality itself. They force us to confront the limits of our current theories and push toward new physics that can reconcile quantum mechanics with gravity. Every weird fact about black holes reveals another aspect of a cosmos stranger and more subtle than we ever imagined. The journey through these 101 weird facts reveals that black holes are not merely cosmic curiosities, but essential clues to the deepest laws of nature. They represent the ultimate laboratories, where physics is tested under the most extreme conditions possible. Understanding black holes may be the key to understanding the universe itself. Our civilization stands at a unique moment in history. We have developed the theoretical and technological capabilities to study black holes in unprecedented detail. The Event Horizon Telescope has imaged their shadows. LIGO has heard their collisions. The James Webb Space Telescope peers into the early universe where the first black holes formed. Yet fundamental questions remain unanswered. Is information truly preserved? What happens at the singularity? Are these objects described by general relativity alone? Or does quantum gravity transform them into something stranger still? The weird facts we've explored today hint at answers while raising deeper questions. The choice is ours, to pursue these mysteries with rigor and creativity. The strange phenomena surrounding black holes, from information paradoxes to quantum hair, from frozen stars to entanglement islands, all point toward physics beyond our current understanding. Time is limited for this golden age of black hole research. The black holes we can currently observe and study are brief windows into regimes of physics we may never access any other way. The data being collected now will shape our understanding for generations to come. The implications extend far beyond astrophysics, into the very foundations of physical law. If we can resolve the information paradox, understand singularities, and unite quantum mechanics with gravity, we will achieve a revolution in physics comparable to relativity and quantum mechanics themselves. Black holes are the universe's way of showing us what we don't know. Every solution to their paradoxes requires new physics. Every observation reveals unexpected phenomena. Every calculation pushes the boundaries of what mathematics can describe. The message from these cosmic enigmas is clear. The universe is stranger than we suppose. It may be stranger than we can suppose, but the human capacity for understanding has proven remarkably powerful, and the tools we've developed give us reason for optimism. The final weird fact is this: black holes may be the key to everything. Understanding these objects completely would require a theory of quantum gravity that could describe all of physics. We may be looking at the Rosetta Stone of the cosmos, encrypted in mathematics we're only beginning to read.